This lecture discusses the double field revolving theory, which is used to explain the not non-self-starting behavior of a single-phase induction motor having simple single-phase winding. So we have seen already this single-phase induction motor doesn't develop a starting torque, and hence it has to be provided with some means to start it. So how to explain this behavior? That is the question today. So we'll see how the motor, is not developing a torque, unidirectional torque, by using a theory called the double field revolving theory. Just we'll look at the two-pole structure at a simple two-pole induction motor. So this is a two-pole structure. So, so this is the rotor, and the stator has two poles. We give an AC supply to that. So the situation was already discussed, and it created flux, and this flux varies along the a single direction, just moving to and fro, and a pulsating or oscillating field is created, or a pulsating field is created. So this red colored directions indicate how the flux varies. We have already discussed that. Now, having seen that, how this happens, we try to take the help of some mathematics to explain this behavior. So let us take take the horizontal axis as the axis where this variation of flux happens. So let it be denoted by, say, some phi t, which is phi t, which is so you have here some phi t. The flux is equal to phi m, say, cos omega t. Okay, phi m cos omega t. So put that way. So let us say right here as the say phi t equal to, say, phi m cos omega t. So this gives some indication. So let us see what is happening. Okay, so phi m cos omega t is a sinusoidal quantity, which is shown to vary. Its values are changing along one axis. So with horizontal plane, horizontal axis. Now we want to split this into two quantities. So this horizontal flux that we just seen, this flux in the horizontal direction, we would like to split. Maybe some realistic way should do that. Draw it. So this almost half. So this is phi m by 2 cos omega t, and say pi m by 2 cos omega t. So both of these adds up, say to so both this add up to this our original what do you call say phi m cos omega t, which is actually the sum of these two. So these two quantities. So you have initially one sinusoidal quantity which is represented by minus sorry phi m cos omega t, and two quantities say phi m by 2 cos omega t, phi m by 2, another phi m by 2 cos omega t. So adding up to the same value again. So they can be thought of as moving or rotating uh, in two directions. So these two quantities, say phi m by 2 cos omega t, uh, can be thought of as some flux vector which is rotating in two, I mean, this in the anti-clockwise direction and the other one in the clockwise direction. Let this have ns if it is the ns speed in the anti-clockwise direction. This obviously is equal to minus ns. So two fluxes which are actually rotating in opposite directions is able to represent this pulsating field. So two constant, almost, I mean, this constant magnitude pulse, uh, which is, I mean, constant magnitude flux, which is rotating in opposite directions. So let us let's say, so let us see it again. So it is as if we have a direction, which is phi, and this what is a phi t, and this is divided into two fluxes rotating, one in the clockwise and the other. So each will be having the same like phi m cos cos omega, omega t, phi m cos omega t, and this also again pi m cos omega. So pi m by 2, obviously, half of it. So this is the situation. So this flux is divided into two. So we now have to explain how that happens. I'll give a little bit explanation on that. Say, see, um, this flux has a magnitude of phi m by 2. This again has phi m by 2. So phi m by 2. And so if it is theta, this is minus theta, obviously. So omega has the same angular velocity and the synchronous speed we are seeing. But if you take at any instant, it will be phi m by 2. You can split into two quantities, phi m by 2 cos omega t along the x-axis at any time, and along the sine axis you have another component, say phi m by 2 sine theta. So this part sine theta. So you can see that every time this uh, this sine component gets cancelled. So one is in this direction, and this other. So what remains is phi m by 2 cos omega again, which is given, which is actually giving the original flux we started with. So this is equivalent. I mean, this means that a rotating, I mean, two fields of a magnitude phi m by 2 each, half of the original field, rotating in opposite directions is actually helping us in the analysis. because we have seen that it is equivalent to that. So a single pulsating field can be assumed as the result of two fields having equal magnitude, and it rotates in just opposite directions. Now, this is the scenario. So you have now understood how it is possible to represent a pulsating field that is, say, in one direction, it moves along, as the resultant of two and two equal magnitude uh, fluxes rotating in two directions. At any time, you can say putting t value gets the instantaneous values. So you can see that this is a constant magnitude and completes the revolution like this. And this, the other flux, say this flux, say we can green, we can attach, so it rotates like this. And so it continues all the time. So now you have a green and a blue, the red circles, which represent two distinct fields rotating in opposite directions. One is in the clockwise. Sorry, this is in the clockwise direction. This is in the anti-clockwise direction. So you have the situation here, the two fluxes rotating in just opposite directions. Now, this you can again take to the three-phase induction motor scenario where you have a revolving field created. Now, there you can draw torque slip characteristics. We have learned how it is possible to draw the torque slip characteristics. So we'll have a quick look at that. Now, say, when it attains, say, NS, we can call that uh, forward slip point, that is 0. It is NS, that is in the anti-clockwise direction. This is it when the rotor attains synchronous speed, it is 0. SF is 0, and when SF is equal to 1, it is at the standstill position, at the starting position. When SF is equal to 2, it is in the direction opposite to this direction. So this is just opposite to the direction. So you get SF is equal to, you can calculate that it is synchronous speed minus the rotor speed divided by, so that is the slip. So you can get that condition over here. So this is, and whereas you can think of the forward, backward, so we'll put another color. Say SB at this point is, it is 0, that is, say, minus NS, so the synchronous speed is different for it. So here SB is equal to 1. It is same for the plus and minus directions. Here you have SB, the backward rotating field slip, at 2. Again, the same kind of situation. So you have basically three critical points in this. So we'll draw that. We'll draw the torque slip. So you have two fluxes, forward and backward. SF denotes the slip values for the forward rotating flux, flux, and then SB is the slip for the torque, rotation, which is produced by the backward rotating flux. So here at starting, you can see that maybe this would we have forward case. We'll take, say, SF is equal to 1, 0. So there the torque is 0. So gradually it increases and it is getting down to zero value or near zero when it is SF is equal to 2. Now, if you consider the other case, that is the reverse rotation, then here SB is equal to 0. So it develops a torque and then passes, and at standstill, this is the position. So finally, it reaches to 0 value. Now here, what you can see is this um, when when we'll when, okay we'll try to get a meaning from this graph. So this is torque and this is slip along the x-axis. T is along the y-axis. So what do you infer from it? So here at this point, this is S values are same and equal to 1. At its standstill, it is we call uh, this uh, equal and opposite torques. So this and this value are equal. They are opposite. So adding up to get 0 value. So if you want to draw a resultant curve, it will be something like this. So some of the black and the purple colors of curves, you will get something like this. So this broken line. And I'll make it a little bit thicker, so it's very clear to you. So this resultant, the middle curve, is the resultant of these two fluxes. You can see that at starting, torque remains 0. So if torque is 0, nobody cannot rotate the rotor. It will stay in that position. So that is why the single-phase induction motor is not self-starting. And you can see that the other parts, two halves, you can split into one, say, we call, say, this direction and this direction. I mean, say this if you're taking as the forward direction or the anti-clockwise rotation, and this as the reverse rotation. You can see that here there is a torque slip curve forming. So it is possible for the motor to work here, but it must escape from this inertia of 0. So if you rotate the water off the single-phase induction motor by some means, so even by external means, by just rotating manually, and then you see that the motor will rotate in that given direction. It will rotate. So if I'm doing in this direction, it will take this torque slip characteristics. It will continue to run in that. Otherwise, if you rotate the same rotor with the supply given, rotate in this direction, it will take this torque slip, and it is. So here you can see that the motor can work, but it must escape from this we call it this 0 point, or where the torque is absent because of this cancellation. Forward and reverse torques are cancelled. So you can see that the single-phase induction motor thus does not develop a torque. That is because of this equal and opposite effect, the starting point, or when S, that is forward slip, and the backward slip becomes equal to 1, you get that the torque, the rotor is stationary. So you must do some other mechanism to push this motor to rotate in one direction, so it is, you will get what this is the resultant diagram in yellow that you can see. If you are able to get some kind of both of these characteristics, any of these characteristics, you'll be able to uh, run the single phase induction motor as any other induction motor or three-phase induction motor. Okay, this sums up the discussion on double field revolving theory, which tries to explain the